Alright, so most of these questions are just really quick one-liners, right? Just true and false, pretty much basically like a sentence of work. I'm just going to run through them really quick. So 1, if ax equals lambda x for some scalar lambda, then x is an eigenvector of a. We see that that fails because if x is equal to 0, this entire expression over here will go to 0 as well, which is not an eigenvector, so it'll fail by that. Lambda is an eigenvalue of a if lambda is an eigenvalue of the transpose AT of a. Right, so we can just take our method of finding the eigenvalues, which is just by the determinant of a minus lambda I, and take the transpose of that, and we see that we get the determinant of a transpose minus lambda I. Right, since these pieces over here go over here, we can say that that is going to be true. If lambda is an eigenvalue of an invertible matrix A, then lambda squared is an eigenvalue of a squared. Right, so then we could say that's true if ax equals lambda x for x does not equal 0, and this is a very important definition, right, because we have that from up here from 1. If it's equal to 0, it'll fail, so for x does not equal 0, then a squared x equals a times ax equals lambda times lambda x equals lambda squared x. That's just distributive property. If lambda is an eigenvalue of an invertible matrix A, then lambda inverse is an eigenvalue of the inverse A inverse of A. That's a lot of inverses. True, right? If A is invertible and ax equals lambda x for x does not equal 0, then we have, right, we can multiply the left side of the left and right for our expression by A inverse, right? We maintain equivalence there. When we have the A inverse times A, we just get the identity matrix, so then we get that over here. Identity of x equals A inverse lambda x, which is just going to go to x equals A inverse lambda x. Right, so from this, given x does not equal 0, lambda does not equal 0, we have A inverse lambda. It's just going to go to lambda inverse x. My lambdas and x's look very similar. I just realized that. All right, anyways. AP equals PD implies that A is similar to D. That is, A equals PD P inverse. That's false because P is not necessarily invertible. Right, so since it doesn't hold generally, we cannot say that that implies. There are cases where it is true, but it is not always true, so it fails. If A is diagonalizable, then A has n distinct eigenvalues. So I gave an example here. An eigenvalue can have an eigenspace with dimension null A minus lambda k, some lambda value in greater than 1. Right, and if so, then we have n minus dim null space A minus lambda k in eigenvalues. Right, so we can have an eigenvalue that has two different eigenvectors. So that one eigenvalue itself has 2, which means that we're going to, or how many the dimension of this is, we can just subtract that from that to find the eigenvalues. You can go both ways. But yeah, so that's it for that. That's the next one. If A is diagonalizable, then the factorization of A equals PD P inverse is unique. This is false, right? So we can suppose we have some eigenvalues that are elements of some set A, B, C. So those are their values for some arbitrary one, with eigenspaces v1, v2, v3 corresponding to this set respectively. So we have v1 goes to lambda A, v2 goes to lambda B, v3 goes to lambda C. Right, so from this we can choose any combination of eigenvalues for our D matrix, right, such that the multiplication out here goes back to A. And how we do that is we would set up our P accordingly, right? So this is an example. From our eigenvalues up here, we can set up a D matrix 1 such that it's A, B, C. That implies that we're going to have our P1. We're going to want to set that up with V1, V2, V3, because we define it up here to be respective. There it is, lambda A, lambda B, lambda C. But we can also have D2 equals BAC, so we're going to shift our B and C, or B and A. That's going to imply that our P2 is going to just be V2, V1, V3, and we can do that so on, so on, so on, however many combinations. Right, so since that is the case where we can have multiple combinations, we're going to say that's false because then it would not be unique. If it were unique, we would only have one, but this is just an example where that fails. any two eigenvectors in the same eigenspace of a matrix are linearly dependent. This is false. Right? We can have dim null space of our A minus lambda I. That's going to be greater than 2, which implies that we can take two linear independent vectors, eigenvectors, from our set. And I give a case here. Suppose we have this matrix over here. Once we do this dim null A minus lambda I after finding the determinant to find our eigenvalue, and then we sub that back in, we're going to get an eigenspace with two vectors, eigenvectors over here. We can see that these are linearly independent, as we cannot take any scalar multiple of this or this to get the other piece. So 9. A is diagonalizable. This is false. Right, we can just take the upper triangle to find that our eigenvalues are along the diagonal like this. So that we have our eigenvalues going to be just lambda equals 1 with multiplicity 3. So when we take our null space over A minus lambda I, we just get this matrix over here. We do REF, which is just subtracting this row by this, which gives us the null space of this matrix over here. We see that we have one free variable, and you can actually just skip from this step to this to say that it has dim1 because it has one free variable. But if you wanted to show it out, you're going to do it very similar to how we've done all of our other null space matrices. We see that x1 is free, right? This is x2, x3. x1 is free, so that means our null space, we're going to set up our corresponding columns, x1, x2, x3. We're going to suppose this is equal to 0. That's how we're going to do the null space. I skipped that step, but this is how you do it. So when we set that equal to 0, we're going to see that we're going to have S is free, so that's just going to be any S element of a field. x2, x3 go to 0 here. So that means what we're left with is just the span of 1, 0, 0. Since the dimension of our null A minus lambda I, we only have one eigenvalue, is not equal to 3, it's just dimension of 1, we can say that it's not diagonalizable, and we can imagine why that is the case by imagining the multiplication. So in order to get the 3 times 3 matrix A over here, we need to have all of our pieces be 3 times 3, 2 times 3, 3 times 3. If it were not the case that this is true, then it would not give us back a dimension of 3 times 3, and so it would fail. Right, we cannot, this is not a valid multiplication. Alright, so that's it for that. 10, this is where I did a little step skipping. So B is diagonalizable, moreover all eigenspaces of B have dimension 1. So once again we have our upper triangle, lambda is equal to 1, 2, 3. So we do our dim null A minus lambda 1, I equals dim the null space of this. And this is the part where you can actually skip a few steps. So we can just recognize that we have one free variable over here. So what that means is it's going to have dimension 1. Since it's only asking if it's diagonalizable and if it has dimension 1, we do not need to show the eigenvectors. That's extra work. So one free variable is just dimension 1. Similarly for lambda 2, we see that it's going to be free. Right, because if we take this, we're going to have one pivot, so it's free there. One free goes to dimension 1 again, and lambda 3 is the same thing, dimension 1. So therefore, since dimension lambda 1 plus dimension lambda 2 plus dimension lambda 3, if you wanted to write this more appropriately, you would say dimension null space A minus lambda 1 I plus dimension null space A minus lambda 2 I, which is just a lot of things to write out, but so you do that. Since it's equal to 3, where B is a 3 times 3 matrix, it's diagonalizable, and all have dimension 1. 11 is pretty much the exact same as 10. C is diagonalizable. Moreover, one of its eigenspace of C has dimension 2. This is true once again. You can see that we have the upper triangle. It goes to lambda equals 1, 2. We have multiplicity 2 for our 1. Right, 2. Therefore, we have the dimension of a null space A minus lambda 1. I goes to dim null space of this. Here we see that this is actually has two free variables, right? This is free, because we can take this row, get rid of this one. So two free variables means that we're going to have dimension equal to 2. Then we do the dim for the other lambda value, which is just going to be 2. We say that we're going to have one free variable. So after we conclude that, we're just going to say that it's going to be dimension equal to 1. And similarly, once again, therefore, since dim lambda 1 plus dim lambda 2, you'd use these more appropriately. I just didn't want to write out that much. Since it's equal to 3, where B is a 3 times U matrix, it's diagonalizable, and the dimension of lambda 1 is equal to 2, so it satisfies that one of its eigenspace has dimension 2. I think the last bit is quite unnecessary. Yeah, so this is this is just the proof that it was asking for. To show that it is true, you do not need to know how to do any of this. I believe if you want to check this out more, you can just look at, what was it, Lay's textbook page 307. It should just be somewhere on the tutorial where that you can find that. But yeah, that's it for that one.